So, see in continuation to this our retrosynthetic analysis, I just would like to have one more small discussion, that is about what you can call as a target molecule. Okay, so I'm sure like everybody knows about what you can call as a target molecules. So we call it a TM. Okay, so how to go with this retrosynthesis of the target molecule? So one can categorize this target molecule into two types. Okay, one is the number of the functional group present. So the number of functional group present. Okay, the second one is, so in this case one can have monofunctional, you can have a difunctional, you can have a trifunctional, etc., etc. Okay, so of the same type or different type. So if it is going to be mono functional group, that means so only one functional group present. Example, you just take a, this is the best example where I have only one functional group. What is the functional group? Olefin. Okay, so I can also have a difunctional group, two functional group of same or different. Okay, and try it. Okay, so that is one type of classification. The other type of classification is that position of the functional group. Where exactly these functional groups are present? Okay, where exactly the functional group, whether the functional group is present 1, 2 position or 1, 3 position, if it is a case of di substitution, 1, 4, 1, 5, etc., etc. Okay, or in the case of tri, so you want what kind of the relationship between the functional group present. Okay, so based on that, one can categorize, your target molecules into two types. One is the number of functional group present, the other one is the position of the functional group present. So in this particular case, I just would like to discuss some examples related to this what you can call the number of functional groups, and the second one is the position of the functional group. Okay, so let me just give you some example for mono functional group. Monofunctional group, you just have any kind of system, as I said. So this is a monofunctional group, means I have only one functional group, which is nothing but the keto group, monofunctional group. Okay, I can also have a difunctional group. Okay, so what is the difunctional group? So if I have a one, okay, this kind of system where I have a carbonyl group and this the keto group. So they are 1, 2, 3. So they are 1 and 3. They are 1, 3 functional group, disubstituted functional. Like this, I can have variety of this system. Okay. So another example, like I have OH group like this. So what are the functional group present here? Both are the keto group. Here is one is a keto group, another is a hydroxy group. Okay. So this is also 1, 2, but not the same. Okay, it is a 1, 2 functional group where the functional groups are keto and the alcohol. So like this, I can have in the case of cyclohexane, cyclohexane ring kind of system. So I can have some R groups. So this is 1, 2. So you have to see what is the position between, what is the relationship between those two functional group. Okay, and if you have the analysis of that, that will be useful for you to propose a suitable retrosynthesis. Okay, so like this, I can have a variety of what you can call target molecules. Okay, I'm not going to discuss more about this. Rather, I just want to discuss about the the functional group. Okay, so the very common functional group in organic molecules are nothing but your carbonyl group. Okay, so I might have discussed somewhere or other the compound containing the carbonyl group. Okay, now let me just give you basic information about these carbonyl groups. So for example, you take this carbonyl group. Okay, having a 2 methyl groups is nothing but acetone. So this particular this molecule, once you this can exhibit in a enolic form. Okay, this is a keto form. This can exhibit in a enolic form. What is the enolic form? Where I have the hydrogen which is going to be in a enolic form. So as a result, I am going to have the structure which is having a double bond and the CH2 group here. Okay, now just try to see the polarity of this compound. Okay, so once you have a carbonyl, as you know, okay, this carbonyl carbon, the oxygen. So oxygen is going to have a delta negative, and this is going to have a delta positive. Obviously, this is going to have a delta negative. So in other words, this is going to be nucleophilic one, and this is going to be electrophilic. Now again, this carbon is nothing but your alpha carbon. This alpha carbon is nothing but is a nucleophilic. So nucleophile. Okay, so that can be easily analyzed by taking this particular example. So you see, this is going to be a resonance structure wherein if you try to deprotonate it, you will be getting a negative charge. Okay, so this negative charge is going to make a double bond, and this becomes the minus charge. So I will be having a negative charged carbon, okay, which is nothing but your nucleophilic carbon, where this nucleophilic carbon can react with another electrophile. So what is the polarity of this alkyl halide? This is going to have a delta plus and this is going to have a delta minus. So obviously this is going to be negative and this is a positive and negative. So nucleophilic attack takes place to results in the formation of what kind of product I will be getting? I will be getting a keto group here, and then I have CH2 and then R group. Okay, so if you want to introduce some alkyl group, okay, what is the position? The position is nothing but your alpha position. Okay, what is the nature of R group? R is going to be a positive charged one. Okay, so you can do nucleophilic addition at the alpha carbon, because the alpha carbon is electrophilic addition at your alpha carbon, because your alpha carbon is a nucleophilic in nature. Okay, so this nucleophilic can undergo a simple what you can call addition to your R group to result in the formation of this kind of product. Okay, so again, if you try to analyze this alpha carbon is going to be a negative charge. Okay, a negative charge. So this negative charge can react with a variety of compounds. See, for example, I have taken this case as alkyl halide, and which results in the formation of what you can call what is this called? It's called alpha alkylation. Okay, so this is my alpha carbon. So I will introduce alkyl group at the alpha carbon. So I can call this is a alpha alkylation. Okay, so I can also do the same thing with a halide. Say for example Br2. Okay, so Br. So this nucleophile which gets generated this attacks one of the X group and this gets eliminated. So obviously if it is going to be Br, this gets added to give rise to this particular product. What is the product? This is nothing but your CH2X, where X could be any kind of halide. Okay, so what this halide? This halide is going to have a positive charge, and what gets eliminated? The elimination is X minus. Okay, so what kind of reaction is this? So as I said, this carbon is going to be alpha carbon, and you are introducing an X group at this alpha carbon, so you can call it a alpha halogenation. So what is needed for alpha halogenation? Alpha halogenation, you need to generate an enolate ion. What is the enolate ion? This enolate ion is nothing but where I am using a base or acids, okay, to generate a negative charge, and I am going to make an enolate ion, this enolate ion is going to add to another substrate molecule to give rise to the product. Okay, so you just generate an enolate ion either by using a base or acid, and then you treat this with either alkyl halide or halogen halide to give rise to alpha halogenation. Okay, it's a very simple reaction. Okay, so this is a what you call say a simple method for you to introduce some alkyl group having a positive charge. In other words, it's a electrophile can be added at the alpha carbon. Okay, fine. So maybe I'll discuss the other aspects. This is a monofunctional group having a simple system, a keto group. Okay, fine.